today is a special day for me. I think this is the third time I've been speaking with Boyang, and this is the first time, and we are giving different talks. So previously, we have delivered talks on Kafka streams and how Pinterest uses Kafka streams at Kafka Summit. And I think in our previous jobs, we have been working a lot with changelogs, and we enjoyed it and we hate it, right? And you can see from our career changes, we end up understanding that I think the databases and state are an important complementary to the changelogs. And that's why we join companies building databases. So without further ado, I will hand over to Boyang to talk about his experience building data ingestion at Rockset.
Yeah, thanks, Lisa, for the introduction here. We can get started. Hopefully, well, this color render seems weird, but yeah, I think that's okay. So yeah, my name is Boyang. I will be talking about real-time data injection at Rockset. Rockset is the company I'm currently working at. So very straightforward agenda today. We're gonna give a couple minutes to talk about what Rockset is. Obviously, not everyone here is familiar with this company. Then we will talk about how Rockset builds the real-time data ingestion for years. Specifically, we want to get an overview and then talk into details about two use cases here. One is SQL rollup. The other one is bulk load. So both are very critical use cases to satisfy our customer needs. And then I'll give some time for questions. Yeah, so let's start with company. What is Rockset? Rockset is a real-time analytical database. We are cloud native, trying to solve the problem of building real-time analytical applications for our customers. So this is like a customer-facing application. So it's not just traditional like a data warehouse. You have a bunch of data scientists trying to run ad hoc queries. This is facing the real-time and high concurrency workload. So we have connections to customers' data sources from data streams, LTP databases, data lakes, etc. We are building a database service, so obviously we choose to support full feature SQL. Yeah, one thing unique about Rockset is we paid a lot of attention to not just the system performance, but also developer overhead. So that's why we have this feature called schema-less ingestion, or we call it smart schema. Essentially, this means that if we have customers using data sources from like IoT, semi-structured, or even unstructured data, as long as this data is inferable, we can infer the schema automatically from the customer's input. For example, like JSON, Parquet, CSV. So all those schemas that can be inferred just based on the data. So we can detect those missing fields or overall the data fields look like. And then last thing is actually a very powerful feature Rockset provides is conversion indexing. That essentially, put it in a simple way, is we index everything by default. So if you give us a bunch of documentations, we will build the row index, column index, and inverted index, or we call it search index, on every single field we can access. So that means no matter if you're running a large scan or a point query, all the query performance should be very good out of box. So that also saves a lot of overhead of developers trying to build secondary index of their database to speed up the query, because we all know that's a painful process and it's not a flexible work at all. So that's kind of like the overhead of running all those OLAP data workloads. And so that's kind of like building the one-to-many mapping from the document to all these indexes. Today's talk is not about this conversion indexing, but just to mention that, because that's kind of like the unique feature Rockset provides here. Definitely, there are a lot of trade-offs between the space and the time here. So that's kind of our way to like scale up your data set, building lots of index, but your query performance will be very good. Architecture-wise, Rockset takes something we call ALT architecture. It stands for aggregator, leaf, and tailor. So you can think about we have a complete separation of all these different components so they can scale up independently very easily. So we have this tailor framework, try to ingest data from different customer data sources. We have, and then they push the data to the distributed log, which will be consumed by Leaf. Leaf will do the indexing of all these documents. And then on the user-facing side, query will be initiated by a component called aggregator to fan out to the leaves and then process the results back to the customers. So that's kind of like a very disaggregated architecture. I will talk 2 user stories really quick because I think, yeah, just to give you guys a more realistic picture of what we're doing here. Rumble is an Israeli company. They are building a healthy app, trying to help their customers develop a healthy lifestyle. The approach they take is they take your daily activities and steps and convert them into some reward coins. So those are coins that actually can be used to purchase some unique products from hundreds of online shops. So it's a very interesting app. And one of their key feature they're trying to support is this leaderboard in real time. So leaderboard is just basically all this kind of athletic apps need to do some social things. So they try to help you get access to your friends, your colleagues' performance as well. So building a real-time dashboard is not so easy. Traditionally, they dump their data to Postgres, and they need to build this hourly workflow, build an hourly table, merge it to daily table, and then weekly table. So everything doesn't happen in real time either. So by changing to Rockset, they can build this leaderboard very easily because they have all this support of real-time data ingestion with just a couple of seconds delay. And then on the query side, we can support high concurrency queries to leverage the converge index as well. Another one is Command Outcome. So this is a construction company. They track these construction hardware's metrics and convert them into the software and then push the data into their platform called Connex. So their customers try to build all this real-time dashboards, ticket data, or just do third-party APIs to support their own customers. Yeah, it's traditionally also very hard with DynamoDB because Dynamo is sort of designed for transactional rights to collect their data, but not designed well enough for supporting a large-scale OLAP queries. So that's why they also leverage Rockset to help them build all this offset source connections. So those are very good customer stories we have built for years. Yeah, as I mentioned, we do have all kinds of different data sources. Streaming means like Kafka, Kinesis, blob storage, Azure, GCS, S3, or data lakes. We also support database CDC. CDC means change data capture. So that's if you have a database table, you need to tail the real-time update to it, and that's the change log of it. So we support Dynamo and Mongo. These are 2 most popular connectors we have, and we are planning to support Snowflake CDC as well in the near future. Yeah. So with all said above, I think it becomes obvious that Rockset needs to build real-time data ingestion, not just a traditional way of ingesting data in batch. Because we detect what our user really want here. There are 2 key things I think our customers need most. One is this real-time delivery of data with all the insights here. So if you think about all these streaming technologies on the market, Spark Streaming or Flink or Kafka Stream, what they've been doing is trying to do the data transformations on the fly. So when you have streaming data, you're gonna produce some materialized views by the end, so that the materialized view is actually what you want, not the raw data sources. So that's kind of like the first thing as our data ingestion pipeline need to help with. And the second thing is these initial onboarding experience with customers. So no matter customer's data set is a couple of megabytes or gigabytes or even 1 terabyte, yeah, those with those large data set, we don't want to give them a bad experience when they have to wait for hours, even days, to index their initial batch of data. So that's why we have to build some bulk load effort to make sure their initial onboarding is very painless. So we're gonna talk about the first solution here, which is rollup. So before we talk about why rollup, we can first talk about what is rollup. So not everyone familiar with the term, but rollup is just kind of doing the pre-aggregation of your data set and do all this kind of transformations of data at the ingestion time instead of the query time. So we can think about if you write a rollup SQL query, then that will be run continuously on the incoming data record by record instead of doing all the crazy computation by the end. So that's kind of saved a lot of the CPU resources when you actually facing the user side queries. So yeah, this pre-aggregation definitely going to be powerful because we have a couple of needs here. Customers don't need the raw data. They usually need just say 10% of the fields from some unstructured or IoT collected sources. They also need to do some filters. So naturally, if we have rollup built into our system, then it's very easy to reduce the storage size a lot. That naturally reduce the cost of customers and improve on the query performance because now you have fewer data set to scan in the real time.
Excuse me.
Yeah.
Could you please help me understand how this pre-aggregation can reduce storage size?
Reduce size wise, yeah, we do have customers can reduce say 10x, even 20x. Because for example, if you have some input data with, I will give an example later, but a lot of like data, like for example, you need a count of some like user activity or stuff. So you don't need to know every single user activity, but if you do the aggregation, you will just end with the aggregation results.
So just figure out a meaning.
Yeah, it's not a filter. It's like just compute the aggregation of like if you run the group by, like the right SQL query, then yeah, you just need the group by result. You don't care about the original result.
Right.
Yeah, so
Makes sense.
no problem. Okay, so yeah, I'll give a quick example. So for example, this say camera capturing the cats and dogs. So we have location, timestamp, and the count of different animals. We can potentially build a rollup query like this. So we have the aggregation based on the event time and the location. Plus we have this count of the cat and dogs in some format of aggregation as we want. And what we're gonna do here is that this is like a preview page of your data source. So when you have the first input from San Francisco and the timestamp, then you have the transform dog into the aggregation result based on, for example, the animal count maximum. You can just sum it up. It gets you the 3. And then the next one came with the same time and location. It will be transformed into the same aggregated dog. So there won't be 2 dogs, but instead by the end you will get 1. And the third one comes with LA and different time. Then you will have another aggregated document. So on and so forth. When there are some different time windows, you can get another LA record by the end of the preview. So that's how we kind of compress the amount of information. Well, essentially, seems not the compression to me because we might produce more fields, but the things we transform here are more valid, more useful information to be queried at the runtime instead of the raw data set. So some of the key design decisions here includes the first is what language to use, and we kind of make no-brain choice to use SQL here because our products speak SQL, or a lot of database customers use SQL a lot, so we don't want to reinvent any new like a feature language here. So all this rollup support will be composed in SQL. And another thing is we are doing real-time ingestion, so we want to build our update to the aggregation windows in real time. So in the traditional way, you build the aggregation batch, then you have to wait until the current ag window to be complete before you can query it. So doing this real-time updates means that you can even access the open windows of the aggregation results at the runtime. So that's kind of we provide the real-time queryable results. And third thing is coming more or less trivial, but it's a very typical problem with streaming system. Always there could be late arrivals or out of order updates. So with the we need to be accountable for all this kind of late arrivals update of our aggregation windows as well. So that's some decisions we made when we designed this project. Yeah. So coming from traditional aggregation to real time is difficult because the implementation will be much more complex. For example, now in your system, what you store is no longer the final state of the aggregation because you have an open window out there. So you have to store something we call it partial state. So for example, if you're computing the average, then you have to store two things. One is the sum, the other is the total count of the record A. So that at the query time, you can leverage the partial state to compute the final state. So that's kind of like some difficulties there. And then let's talk about some challenges in the implementation. So first is the query decompose. As you can see, the partial state computation needs to come at the ingestion time, but the rollup query itself could go beyond just the partial state generation. So we have to be smart about detecting inside this rollup query which part of the work is suitable to be done at the ingestion time and which part is to better be done at the query time. So here, the ingest query will be the part we separate out from the rollup query to be run on the continuous ingesting data. For example, like if we do partial state aggregation, simple math computation and stuff, and the group by. So those are very straightforward things we can compute at the ingestion time. While on the other hand, we separate out the query, the wrap query. So wrap query means that this is sort of like a view on top of the aggregated results. So when user sends their own query to the collection, we will apply the wrap query at the basic level so that we can give them another high-level view of the data set. So for example, if you have some more complex computation based on the aggregated results, then that won't happen at the ingestion time because it's impossible to get aggregate result there. So we need to be able to parse out this wrap query. So yeah, just using the same rollup query example. Everything I highlight here in yellow are going to be the ingest query because these are straightforward partial state computation. You don't have to know the full picture to give out the results. So basically, if you give the couple of raw documents, what you transform to will be just based on the partial state aggregation, and the stuff you store in the leaf will be later used for the user query. So these are not directly exposed to the customer. So customers are not visible to this partial state. While on the wrap query is this crazy metric computation. So you take some square root of the aggregation result and do some multiplication. Those are not something you can compute record by record. So that's when we detect this is no longer the part going to be put in the ingest query, but something we put on the wrap query. So wrap query going to end this state into what user actually want. So like I said, if you have the transform doc, then at the query time, the wrap query will be used again to compute this crazy metric. And what we're going to be exposed to customers is just the crazy metric, not this partial states. So yeah, another challenge here is how we execute this SQL ingest time. This is just recap about our pipeline for ingestion. We have Taylor get the data from customer data source, push to distribute log, and then tail by leaf. So there's no place Taylor can have access to any component in the service to speak SQL. so that we definitely don't want to reinvent the wheels in the Tailor to build another SQL parser. So that's why we have aggregator into the picture. Essentially, used to be aggregator just talk to leaf, but now we build another RPC layer like between the Tailor and aggregator. So for the rollup purpose, and with that, you can basically let tailors send a batch of the raw documents to aggregator. So aggregator already speaks SQL, it understands a rollup query, and then it can compute the transform documentation, send it back to Tailor, which will be then pushed to the distribute log by Tailor. So that's kind of like our way to solve this tricky problem. Yeah, so performance-wise, what I heard from my colleague is that this is actually pretty good because we can do pretty good batching there between the Tailor and the aggregator communication. Then handling the auto-order variables, or say how we update one aggregation group in the runtime. It's actually kind of like the same problem statement that with rollup, you could have the same document being frequently updated to get new partial states. So it doesn't matter if it's a late arrival or not. But some sort of like a patching or upsert semantics needs to be supported with the rollup. So we do this by making sure that all the updates to existing aggregation group always go to the same leaf. So that's kind of like a data partitioning scheme here. We have a _ID field, used to be the primary key in the data collection. So all the rollup collections will be hashed based on this grouping dimensions, so that you can use this _ID field to know the exact leaf you should push your update to. So for example, our rollup query with cat and dogs, we are grouping by event time and location, and then we can build the _ID with 128-bit hash of event time and location. So that makes sure any single partial state update going through our pipeline will be landing in the correct leaf. Yeah. So we do some sort of read, modify, write semantics with all this upsert documentation. So essentially, we store leaf stores the data in RockCB. So when we have a need to update existing documentations, we'll just load the doc into the memory and patch it, and then send it back to RockCB. And last thing is actually a bit challenging here is something we call exactly once, right? So if you come from some streaming system experience, you're familiar with the term, but it's actually something like in a higher level that's like a semantic which is much harder than the traditional two popular semantics, one's at least once, one the at most once. So when we say exactly once semantic, put it simple, it just means that every single event or record flowing through a system will get processed once and only once. Traditionally with Rockset, we are a secondary database. We already support at least once semantics with our Tailor framework. Because we have regular checkpoints on the Tailor. So even if Tailor crashes, we still know we already pushed the data. So that's sort of like at least once semantic already supported. But since we introduced rollup as a new feature last year, this framework is no longer like reliable enough to be able to support rollups, because with rollup you cannot apply the same update twice. That will give you the wrong aggregation result. So you need something stronger. And similarly with all the streaming data sources, there's like a strong need for the data process ordering. If this is from the same stream partitions, you want to make sure that they are processed in order instead of kind of in wrong semantic. So to support that, we introduced a new concept called update ID. For every single update we push to the distribute log. So this is something we infer from customer data source. For example, if this is Kafka data source, the shard ID will be Kafka partition. If this is a Kinesis, it will be the Kinesis shard ID. So with streaming sources, usually if you have the shard ID and the sequence number, which is just the record offset. So with combine these two, you can build a monotonically increasing sequence like identifier of your updates. So basically that's going to be very useful to reject any sort of duplicate updates. So on the leaf side, anytime we see some update with a sequence number lower than our current record sequence number, that means this is already something we apply in before. We don't have to do it again. So that's kind of a way to reject any sort of duplicate writes. And this metadata will be also persistent in ROSDB.
Hi, may I know who will generate the sequence number?
Sequence number is generated by Taylor because Taylor just reads from customer data source. So we are not responsible for building update ID. We're just extract those information from customer data source. So if customer data source, like if their Kafka has some bug, then we cannot solve it. So yeah.
Okay, so each Taylor will generate its own sequence number. Is that right?
Oh, the sequence number is also from the user input data source. Like Kinesis and Kafka already have offsets. So we just take advantage of that.
Yeah, I think the question is about like, is it global order or is it partial order?
Yeah.
It's a partition order.
Partition order.
Yeah. It's not the global order.
Partition means the data source.
The data source.
So the data source needs to guarantee the uniqueness and the global.
Yeah.
Okay.
Yeah.
So you just leverage the feature based on the source given.
Yeah, but we do have internal sharding as well. But essentially, with this external information is good enough to make sure we don't have duplicate updates. Yeah. Mm-hmm.
How do you ensure that the data sources have the unique ID?
So far the data source we process. I think even with S3, there's some way to infer the unique IDs. We currently support Kafka, Kinesis, and S3. I'm not sure if we have any data source right now that purely rely on Rockset to build the unique ID. But even later, we want to support that. I think unique ID generator is not like magic. Yeah, it should be not hard to work out. Yeah.
Actually, most of this we have some sort of unique ID to be used already, so it's all on box. But who knows in the future?
Yeah, for sure. Yeah, I mean, I'm just saying, this is not like a free lunch, but yeah, essentially it's not that hard. So yeah, just quickly summarize the rollup case here. We on the right path we decompose the rollup query to the ingest query and wrap query. Ingest query runs on the aggregator. Taylor send raw documents to it and get back the transform doc, then being sent down to the distributed log. Distributed log will be tailed by leaf and then process updates. So like we talk about update ID, then on the leaf side, we have at most once ingestion, and on the Taylor side, we have at least once. So end to end, we can build this exactly once right semantics. On the read path, you can think about wrap query as a view on top of the transform documentations. So we only expose the end state to the users by applying the wrap query at every single query they run. So that's how we overall build the rollups. Cool. I think let's get to the second use case and we can ask questions later. So that's something I just talked about with the large data set onboarding. So we call this phase bulk load. And just inferring from the name, it just means that if you were given a large data set from customers, say over 100 gigabyte, usually the indexing time could take hours. And it make the first time user very impatient about it. So they kind of see this indexing time forever. And when they send the query, they only see the partial data. So that's not a good use case there. So we also know that this indexing time almost completely depends on how much CPU can be used on your data source. So we kind of invent this new data ingestion phase to optimize the initial write time here. because if you can spin up a whole bunch of large machines and try to leverage as much CPU as you can, then you can quickly index every field and then make this collection queryable. So for years, we built this orchestration framework, tries to like automatically detect any need for doing bulk load. So imagine if this is an S3 data source, then there's an ingester coordinator, try to monitor the data source size. If it sees the size is pretty big, and right now the default is 5 GB, so that will trigger a bulk load phase on the ingestion. With the bulk load phase being triggered, then the downstream after the distributed log will not be using the normal leaf, but we create something called the bulk leaf. So bulk leaf is something more powerful than the normal leaf, which is targeting the use case of building the ingestion and optimize the write throughput. Ingester coordinator then inform the worker to kind of do the like a batch scans and try to optimize the initial dump speed. And then it will send a CO record by the end when it saw you have seen that the shard has completed the initial dump. Then this message will be also tailed by bulk leaf on the distributed log. So that will trigger a final compaction of this specific data shard. Yeah, we'll talk about the compaction later. But we kind of disable the raw CP compaction along the indexing phase and only do one final compaction by the end. So that's kind of another optimization for us to make sure we can quickly turn around on the initial data ingestion. Yeah. So yeah, like I said, bulk leaf, nothing fancy, just a different type of machines which can process a lot of data shards in parallel to speed up the initial dump, initial indexing phase. And then we're gonna talk more about the optimizations we take in the bulk array. So just recap on the theme here. No worry about throughput. No worry about latency. Only throughput is the goal. So we during this period we don't expect any customer queries, and we actually explicitly disable the customer queries during the initial bulk load because this data set is incomplete. There's no meaningful reason to query some sort of data set like that, and try to leverage all the cores available on the bulk leaf. So Taylor write, the leaf write path is pretty straightforward. You take from the distributed log, you build your documents, and then you insert raw CP. So that's like a normal streaming updates path. But with bulk load path, we're gonna take a couple of optimizations in each of the individual steps here. So for example, on the Taylor side, we completely remove all the rate limits on the streaming ingest. So we have our service model is something like a virtual instance. So based on your type of virtual instance, we'll give you a corresponding rate limit. But with bulk load, we just remove that, and also we build a much bigger like batch size to process on the leaf. Compared with the traditional streaming way, because we don't care about delay anymore. The delay can go up to minutes or even tens of minutes. That's totally doesn't matter. So we can optimize for the initial write throughput. And then during the document generation phase, we use multi-threaded writes to make sure that we can process a lot of records at the same time. We also have something called the micro shards to further split up the existing data shard so that each worker can work in parallel without any global locks. And then, yeah, this is something pretty unique here. We disable compaction because I think everyone who are familiar with RockCP knows that compaction usually is your CPU either. Yeah, you kind of, they give you surprises all the time. So somehow you fall into the compaction loop, and then all your CPUs has to be used towards that. So disabling all the compactions during this period means that you get a whole bunch of SSD files laid out on your disk. But that's okay because our use case here doesn't require you to query your raw CP at this moment. So this is like a fully write optimized situation. And if you do all the compaction by the end, another benefit you can get is you already free up all the cores you have on the bulk leaf so that you can use the multi-threaded compaction provided by RockCB to speed up the compaction phase as well. So, but there's no free lunch again. So we disable compaction. There's another problem, which is how we find the primary keys. Because this, even before rollup, we also support upstart or patch semantics from customers. So they expect to be able to update their existing documents. So to do that, they have to do a primary key scan. And then because you have too many uncompressed files, then this scan could take a very long time. So we built a bloat filter on the primary keys so that you can very much speed up your primary key lookup on all this compacted files in RockCB. So that's another optimizations we take. Yeah, and then last thing is we disable the mem table during this phase because RockCB already provides a very useful feature called ingest external file. That just means that you can just build SSD files yourself and then pre-compute all those files and ingest through RockCB. So you don't go through this single-threaded, slow mem table inserts, mem table flush phase during the block write time. So yeah, I mean, conclusion is pretty obvious. We kind of get much better performance on ingesting a large data set. So yeah, that's it. And then yeah, that's the 2 use cases I have today. And I will always recommend people get your hands dirty after tech talk. So if you want, you feel free to go through Rockset and create an account yourself. We have a free account and you can try the SQL rollups yourself. Yeah, this pretty powerful features, and our products is very easy to onboard. Yeah, unfortunately, I don't think I have a demo today, so yeah, feel free to try it yourself. Yeah, and also get some reference by the end for all the things I talked today. So feel free to check for details. Yeah. Yeah. Any questions?
Questions from the audience? Yeah. Any questions online?
I have one question for the bug load. There's a bulk leaf node. Is that something the user needs to revision, or it's on demand?
No, no, it's like we do it automatically. Yeah.
Okay.
Customers
like service.
Yeah, but we will let customer know the cost with that. So if they are onboarding something like 1 terabyte, we'll give them a heads up because all these machines are very expensive. So if they truly want to optimize for it, we will give them these machines. But if they don't want it, we can disable the feature. So they can do more slow ingestions as they want.
Okay, so is that charged by provision or charged by usage?
It's charged by it's like it's charged by the CPU hours. Yeah, I'm not sure it's a provision or usage. I would say more provision. Yeah, because yeah. Oh, actually, usage may be more accurate.
Basically, you charge by like by the CPU hours, by the data.
Yeah, for example, this machine spinning up takes 6 minutes. The first 6 minutes is not chargeable. Yeah, we don't charge customers.
So we don't charge the number of like the data volume, but
that's our cost. Yeah. So
cool. There's a question online, and the question, I will read the question out. Will there be any data skew problem on the leaf aggregator Taylor node? Any node needs to run computation job, and how's that handled?
Well, that actually comes to more a question about how Rockset handles the converged indexing. So we actually do something different than the traditional database sharding, which is we have this same piece of data, and then we don't like based on the we don't like partition, but we actually build all the index on the same piece of data. So all the things I mentioned, the row or column or inverted index will be built on the same piece of data. So you don't shard it anywhere. So this is a very risky trade-off here because every single time, if you say have 100 shard, then your aggregator needs to talk to 100 leaf. So that will give you like a slow performance in theory that you will be dragged down the performance by the slowest responsive leaf. because every single query you need to fan out to 100 clients. But in the meantime, the perk here is that you will be able to leverage 100 machines, like a computation resource in the real time to compute your query. So if your query is a large scan, then you can fan out to 100 pieces, and that will be kind of very beneficial. So that eliminates us from the data screw problem. Yeah. So.
Okay. This question, I believe the question is that, is the data ingestion process resumable? For example, if there's a problem at 50% progress.
Yeah, we do have a pause feature. So for some reason, maybe customers don't want to continue ingesting data, or the data source has some problem, they can pause it and then resume. We already have all the checkpoint framework implemented in the Tailor. So yeah, the Tailor knows where the last ingestion stops. So.
Any further questions? Okay.
Cool. One more question. Sorry. So after the bulk leaf process data, will you move data from the bulk leaf to the normal leaf?
Yeah, we all the Rockset shard data are back in S3. So once the RossDB compaction is done, and then we will upload all the SSC files to S3, and then the shard scheduler will be able to like coordinate all the spinning up of regular leaves, spinning down the bulk leaves. So regular leaves will download data from S3 and start. Yeah.
Okay, got it. Thanks.
Yeah.
Hey, one question. So the intermediate result is placed on not on the S3. Yeah. I mean
the result of the compaction.
Yeah.
Yeah. After the final compaction, we upload to S3.
Yeah.
Upload
but before upload, it plays on like local disk.
Yeah. So if for some unfortunate reasons, like if we're on the spot instance and that gets ripped off by AWS, you have to restart the whole process. So that's like a pinpoint of the framework, but we're trying to see if there's any other better solutions. Maybe doing some partial updates to S3, because right now, like if your total job is 1 hour, then you crash by minute 59, then you have to restart all over again. Yeah.
Okay, cool. Okay, before I start my talk, I'll do a very important step out here. So we have some speaker, I think specific or speaker tailored swags. I think this is we have this I think bottle, and this it can keep your water warm. Not we have this T-shirt.
Yeah.
So I think if you are interested in getting this swag, you can encourage to give a talk at this meetup. So this is for you.
Okay. Thank you.
Okay, we will upload the video to YouTube. We have a YouTube channel.
Okay, yeah, let's get started. So can the people online hear me clearly?
Yes.
Cool, thank you. So today's talk will be data migration the TiDB way. I think it's a continuous of my last talk. I talked about microservice TiDB way. So I believe some people may heard about that talk, but for people who haven't heard about the talk, let me start with my introduction, and then I will quickly recap what I covered in my last talk. So I'm Liquan. I'm currently a senior database engineer here at PingCAP, and prior to joining PingCAP, I've been working at Pinterest, Confluent, working on Kafka, Spark, and I think I would repeat one of my fun facts. Before I joined PingCAP, I have 0 years of working on a relational database. I've been working with distributed logs and NoSQL databases. So I think in the last talk, I covered about the heavy problem people want to see is basically growth. And this is good for people who are building the application, but it's a challenge for the databases because there will be a lot of pressure on the database. And then I also talk about in case you encounter the heavy problem, you should use TiDB instead of sharding or adopting new SQL. And then what is TiDB? TiDB is a distributed SQL. It's no more manual sharding. It is MySQL compatible and is horizontally scalable. It offers high availability. It supports HTAP transactions. And it's open source. It can be deployed in any cloud providers. It is not a fork, not a middleware, not SQL on Hadoop. I think here you'll probably already be interested in what TiDB is. And I encourage you to check out my last talk, which is available on this YouTube video link. And then here I want to quickly recap what is TiDB's architecture. It is a layered architecture. It has a SQL layer that taking the SQL queries issued by the application. And it has a column store and a row store. And that's why we call TiDB an HTAP database, because it can support both the transactional queries and analytical queries. And it's scalable. And yeah, you can see from it. So, but I think this is good, right? We have a scalable database, and you can use it to handle your growing workload. But I think there's a very important problem people usually forget. You still need to get the data into your database, right? Everything's good, but you cannot get in your data to the database, then nothing can work. So I think today my talk will be focusing on how can you use the tools provided by TiDB to migrate data and application to TiDB. Here's our goal. Probably you will have an application building on top of MySQL, and then your application grows. You may also be the unfortunate folks that already started the application. You already experienced pains, and you don't want to do it anymore. And our goal is to have your application migrate TiDB for both two scenarios. Simple enough, right? How are we going to do it? So there are a couple of steps. I think the first step is we typically will create a SQL DAM from your MySQL instances, right? So this is create a lot of files, take it down. And the second step is that you need to load your initial DAM to the TiDB. And your TiDB now have your state probably equivalent to a point in time of your MySQL state. And then it will be streaming the change events from your MySQL to TiDB. And the goal is for your TiDB to catch up those changes so that within a certain time, your TiDB and MySQL is close enough, and then you can make the switch. Importantly, because your MySQL holds a mission critical data, and you have your MySQL running on supporting the mission critical applications, you don't want your process, your application to be wrong once you migrate to TiDB. Then an important thing you need to do is that you need to continuously verify the state of your MySQL and in TiDB to ensure that they are the same, so that there will be no corruption once you switch over to your application to TiDB. And then you're confident, right? Then you switch your read path to use TiDB because you make sure that the data is already like in sync, but then you don't want your something on the right path that correct your data. Then you switch your read to TiDB. But still, your MySQL will take the writes and then you stream the change events to TiDB. And finally, you are confident enough that you will switch all your writes to TiDB. Importantly, because these are critical applications, you want to have a bit of extra cautious. And typically, once you've done this migration, your app is already have your read paths and write paths on TiDB. You still want to have a backup. And typically, now you have your TiDB streaming in the events back to your MySQL so that if anything unexpected happens, you can always switch back. And to summarize, here's the data migration process. First, you create the initial DAM. Second, you load the initial DAM, and then stream the changes. you want to continuously verify the upstream and downstream, and then you switch traffic. And this is a step. And this is a pretty simple process. However, this is not very trivial once you have done things in scale. When you start considering TiDB, you probably already have terabytes of data or a couple of terabytes of data. And then the process becomes painful because if you think about how many hours you need to dump the data from upstream MySQL to your downstream, it will take a couple hours, even days, depending on the volume. And the second thing is that your MySQL is still running, still supporting your online traffic. When you do this dumping or do this streaming, how do you make sure that the impact is minimum so that your user won't see this, right? You're loading your website and you cannot see the result because your database is dragged down by those data import, data migration traffic. And the third thing, you don't want to have data corruption. Once you switch and your user may see the wrong balances and they may see like something not be readable. So those will be a disaster. You don't want that. So that comes to another thing. We want those tools we built in TiDB so that to make your data migration path to be smooth and easy, and you are always covered. So what tools TiDB offer? So TiDB offers TiDB dumpling, TiDB lightning, TiDB DM, and SyncDiff inspector to cover the steps I just mentioned. So dumpling is a tool that allows you to take an initial dump at scale for your upstream MySQL instances. And TiDB lightning is a tool to fast import data to TiDB. And the TiDB DM is it's a tool to continuously sync the data between upstream MySQL to downstream TiDBs to ensure they're caught up. And then we have SyncDiff inspector that continuously verify the data in TiDB and MySQL to ensure they are in sync and there's no data integrity issues. And what is TiDB dumpling? It is actually pretty simple. Think about what it takes to dump a SQL database. It's basically a giant loop of select everything on every databases, on every table, right? That I think I did that. But it's not the case, not that simple. Because if you do that, it'll probably take forever when you try to download multi-terabyte of databases. And that can also have big impact on the online traffic. Then typically we'll do a parallel processing, and we also offer threading rate limiting on the tools so that your online traffic is impacted in a minimal fashion. So here, the example is that for table 2, we partitioned by the primary key, and then we run those loops in parallel and generate the CSV or SQL files. That can be imported using TiDB Lightning later. And I think here I want to mention one thing. So here the importance is that we want to take a consistent dump so that once you do the stream changes, you know where to start. And there are a couple of things you need to make sure that the dump is consistent. There are a couple options for different databases. I won't talk about them in detail, but the goal is that you need these options to ensure that your dump is consistent, is globally consistent. And then TiDB Lightning. So TiDB Lightning is pretty simple. It takes about CSV data of the SQL dump generated by Lightning or other mechanism, and then write them to TiDB, right? Take the data that can be from local files system, or they come from a global storage like S3 or GCS, and then write them to TiDB. That's also very simple. But then there are different ways of writing to TiDB. So the first thing is pretty simple. Because TiDB is a SQL database, you can basically insert data into the SQL database. Once you have the SQL file or CSV file, Package file, then you can convert them to SQL insert statement and then write to TiDB, right? Things solved. Here I have a question to the audience. What do you think are the problems with this approach?
You have latency?
Yeah, latency probably is good, but it's also not a big concern. Any guesses? What are the problems with this approach?
Is there any like syntax mismatch?
Yeah, that can be. But think about this, right? I mentioned that this is a process when we do the initial load the initial depth. And when we load the initial depth, there's no data in it, and there's no read and queries on the database. And in this case, when you do insert, you still have to go through the transaction protocol. You still have to go through those checks, make sure that there's no conflict, make sure that there's data integrity, right? There's a lot of unnecessary things you have to go through if you do the inserts, which is not optimized for this process. And so this is TiDB backend. So we've heard another backend, we call it the local backend. Remember, I said at the beginning, TiDB is a layered architecture, and we have like a storage, O storage is a key value storage, and we call TiDB. And given that we know there's no other kind of like ongoing transactions happening in the database, we can basically take an optimization that we will just generate the sorted pairs and create those SSTs and ingest data physically without going through the transaction layer to speed up the kind of data import. So this is a very important optimization for the initial data loading. And this is also a recommended like way to do data import for the initial data. So as I said, it's pretty simple with the sorted key value pairs, with SST files, then physically ingest those data to TiDB. And how to select backend, as I mentioned. So I think the local backend is faster, but it also has more resources, because you need to sort the data. And then you probably need a large memory in order to do global sorting and things like that. And it also requires data to be empty in order to take this like optimization. Otherwise, you may run into data integrity issues. On the other hand, so if you have TiDB backend, you can do incremental load because that goes through the transaction protocol. You can guarantee those data integrity, but then the challenge is that it's much slower because you have those overhead of going through the transaction layer. So that's lightning. And then the important thing that, remember that we are handling those data import at scale. Potentially this import can take like hours or days. And there can be things happening, there can be hiccups in your environment so that your data import can be interrupted. And TiDB Lightning already take care of this and it provides checkpoints. And with checkpoints, you can continue importing from a very left off. And then the checkpoint can be saved in local file. It can also be saved in MySQL compatible databases. And the goal is that during the import processes, you can always resume the import. Next, I'll talk about the DM. DM is a service. And the majority of goal of the DM is basically we tail the bin log from upstream MySQL and then create the SQL queries and then write the data to TiDB. And this process is basically called the incremental data loading. So this is different from the initial dump load because we already have data in TiDB, and then we have to go through the SQL layer. So the way we handle it is that this is an ongoing service, and we have a master that basically do task assignment and the load balancing, and we have DMAP work actually tell the data and then write the SQL query to TiDB. And then last, I'll talk about the data verification. So we provide a tool called the SIMD Inspector that compare data stored in the databases with the MySQL protocol. It can compare the data in MySQL with that in TiDB, or the MySQL with MySQL, or TiDB with TiDB. And basically it will tell you that which data or which table are equivalent and which table are not equal. So I think those are tools I quickly go through. And then I think after you use these tools, you migrate the application, you end up either with this architecture or with this architecture. So for this architecture, because your application already with running on TiDB, and the TiDB has row store and column store, and with those, you can not only support the original application, but it will also run analytical queries to support the real-time dashboards. And even during this migration process, even you haven't decided to switch your application to TiDB, your TiDB can still serve the analytical queries and support those real-time dashboards. Yeah, because that has already caught up with the upstream data, and then you can run your aggregation queries on those dashboards to facilitate reconciliation or generate some leaderboards, things like that. And we actually built a website that actually utilizes TiDB, utilizes its full capability to support both the transaction queries and the analytical queries, and we call it OSS Insight. And the website is ossinside.io, and you can use it to see the trends on the open source and figure out who are the popular applications or framework in your open source. And that's all my talk.